we saw that to change velocity was to either change its speed or change its direction. Changing the speed causes an acceleration in the direction of t, the tangent vector, the unit tangent vector. Changing the direction causes acceleration in the direction of the principal unit normal vector. So what we're going to do in this section is we're going to take our acceleration and we're going to decompose it into two vectors. One will be in the direction of the normal vector, the principal unit normal vector. The other will be in the direction of the unit tangent vector. That will show us the quantity of the acceleration that's causing the change in the speed and the quantity that's causing the change in the direction. So we'll be doing projections onto the tangent and the normal vector, getting those two components for the acceleration. So now, acceleration vector of an object moving in space along a curve has the following representation. Now, a sub t will be the component of the acceleration in the direction of the tangent, the unit tangent vector. The a sub n will be the normal component, which is the amount of the acceleration that's actually being accomplished in that principal unit normal vector. So these are just the two components of the acceleration in the tangent or in the normal vector. Now to find the a sub n, that's that change in the direction. We saw that a sub n was equal to one of these two forms, where you were looking at the change in the direction. The a sub t, now if you have the function s of t, or r of t, we can simply take that second derivative. We also had a formula for it where it was the dot product over the magnitude of v. That's where you're just taking the acceleration and taking the dot product of it with that tangent vector. Remember, v over the magnitude of v is that unit tangent vector. So let's see how we can actually find these components. First, looking at a graph, if this is our acceleration, the vector representing acceleration, we can decompose it into two parts. One part is going in that tangent vector, so we're looking at that projection onto the tangent vector, and the other part is a projection onto that normal vector, the one that's pointing on the inside of the curve. So each time we're taking this and we're going to be projecting it onto either n or onto t, and those two, n and t, are orthogonal to each other. So they're the components of that acceleration vector in those two directions. Okay, let's say that we have a driver of a car that's following a parabolic trajectory. So the curve is this parabola given by r of t is t squared, and that's for p equal from -2 to 2. So I want to find the tangential and the normal components of the acceleration. So first, to find the tangent portion, let's find t of t first. I want to find the actual unit tangent vector and the unit normal vector. And then we'll see how acceleration is decomposed into those two parts. So t of t, we know, is r prime of t over the magnitude of r prime of t. R prime of t will be 1, 2t, and the magnitude will be square root of 1 plus 4t squared. So now let's find the normal vector, n of t. We'll use the formula, the change in the tangent vector with respect to t over its magnitude, since this needs to be a unit vector. Now, the change in t with respect to t, that's just the derivative of t. So t prime, now keep in mind, this is the same thing as 1 over the square root of 1 plus 4t squared, 2t over the square root of 1 plus 4t squared. So the derivative of t, now we need the quotient rule. If we want to take the derivative of this, 1 over the square root of 1 plus 4t squared, the quotient rule is I'll square the denominator times the derivative of the numerator minus the numerator times the root of the denominator, which is 1/2 times 1 plus 4t squared to the negative 1/2. Running out of room. And then we'll have times an 8t. So I'll have negative 1 times 1/2 times 8t times 1 plus 4t squared to the negative 1/2. So simplifying, that's minus 4t over 1 plus 4t squared to the 3/2. I'm just bringing this one down to the bottom. I have a 1 power down here. So that's just the first part of that derivative. So we'll have minus 4t over the square root, over actually the 3/2 power. And now the second part, the derivative of 2t over the square root of 1 plus 4t squared. Again, quotient rule. Okay, now I'm going to factor out the 1 plus 4t squared to the negative 1/2 out of the numerator because I have that common factor here and here. Here we have a positive 1/2 power and here we have a minus 1/2 power. So when I pull that out, I'll have one of those left. So I'll have 2 times 1 plus 4t squared minus 8t squared. It really simplifies pretty nicely. This factor can move down to the bottom. I get 3/2 power. And on the top, when I expand out what's in the brackets, I'll have 2 plus 8t squared minus 8t squared, so just simply 2. And now I need the magnitude of that. Hopefully that's not too bad. The square root of the first term squared, which will be cubed on the bottom. So I'm going to have 16t squared over 1 plus 4t squared cubed plus 4 over 1 plus 4t squared cubed. So I've got 16t squared plus 4. If I took a 4 out of that, I'll have 4t squared plus 1, for parentheses, 4t squared plus 1, which then I can simplify in the denominator. So this whole denominator becomes 4 over 1 plus 4t squared squared. Now that's under the radical though. So that actually will be just 2 over 1 plus 4t squared. So now when you divide that into each of the components on the top, we will end up with a minus 2t. Now I have just a single power of the 1 plus 4t squared, so I'm going to end up with the square root left. And then just a 1. Okay, and that's your normal vector. Now if you want to pull out that 1 over the square root of 1 plus 4t squared, you can, and you would have the vector minus 2t comma 1. Same thing with this one up here. If we took out this, we would have 1, 2t, and down here we would have negative 2t comma 1. So really not too bad once you simplify. Okay, now I've got the tangent and the normal vectors. I can easily find the acceleration of this curve. This is our position function, so that means the velocity is the derivative, which is 1, 2t, and that means the acceleration is simply 0, 2. So I have that acceleration vector. I want to figure out how that projects onto the tangent and the normal vector. So looking at a certain point here, the tangent vector goes along with the curve. The normal vector would be going on the direction that the curve is changing. That acceleration is 0, 2 all the time. 0, 2 points directly upward, like that. So what we're going to do is we're just going to take that vector A and project it onto N and project it onto T. And that will give us the two components of this vector that are going in each of these two directions. So this one should be something like that because it needs to come down, so it needs to be a little longer than what that tangent vector is. And then the normal vector, well, it's probably pretty close to that, almost the same length. So this would be the component or the projection of that acceleration onto the normal vector. So let's see what those come out to be. We're just going to simply do a dot product. Well, the formula wasn't just a dot product. If we want, the a sub n is actually that length of that normal vector. So it's, remember the terms, the scale of a onto n, which is the a dot the normal vector over the magnitude of the normal vector. But remember, the magnitude of the normal vector is 1. So this is the same thing as just a dot n. Okay. The same thing for the component of the acceleration in the tangent direction. We're going to do a projection. Well, the length of this, the a sub t is actually that component because we're taking the a and we're doing a sub t times t plus a sub n times n. So we're finding these components, which is the magnitude of those vectors because n and t are unit vectors. So this will be the scale of a in the tangent vector in the tangent direction, which is a dot t over the magnitude of t, which again is just a unit vector, so that's just a dot t. So once we have that acceleration vector and we have the t and the n, we can just do dot products. So let's take a dot n, so a sub n, which is a dot n, which will be that vector 0, 2, dotted with the normal vector, which was, I'm going to go ahead and put it in this form, minus 2t comma 1, to make it a little simpler, over the square root of 1 plus 4t squared. So when you do the dot product, the first components multiplied will be 0. That gives me just 2 over the square root of 1 plus 4t squared. The dot product, a dot, well, the component in the tangent direction, which is a dot t, will be 0, 2, that acceleration, times the tangent vector, which is 1, 2t over the square root of 1 plus 4t squared, which will just be 4t over the square root of 1 plus 4t squared. Okay, so if we actually wanted to show the decomposition, a sub t will be 4t over square root of 1 plus 4t squared times the tangent vector t, which we could use this in its place, plus the normal component, which would be 2 over the square root of 1 plus 4t squared, times that normal vector. So this is the quantity in the normal direction, and this is the quantity of acceleration in the tangent direction. So we've just decomposed that acceleration vector into the two components, and that's the quantity of each of those two vectors that would make that acceleration vector. One thing you can do to make sure that you've got it right is if I take this vector t and put it here and take the vector n and put it here, I'd better come up with 0, 2. This is just a decomposition of the acceleration vector. So that sum should equal to 0, 2. Now this example, I can do it with the formulas, or I can just do it a little easier. I have the acceleration is the a n times n plus at times t. The formula for a sub n, one of the formulas was the curvature times the magnitude of the velocity squared. And one of the formulas for the tangential component of the acceleration was the second derivative, so the change in speed relative to time. Okay, so now let's look at what each of these components are. We know that we're given r of t, r prime of t will be the square root of, do it again, I'm trying to find magnitude. R prime of t will be minus r omega sine of omega t. Don't forget the chain rule since we have omega there, it's composition. And then we have r omega cosine of omega t. So the magnitude of r prime, which is our v of t, will simply be r omega. Now this is a circle. Remember, the curvature for a circle is 1 over the radius. And the radius of this circle is actually just capital R. So the curvature is 1 over the capital R. So we have the curvature here is 1 over R. The magnitude of the velocity squared will be r squared omega squared. ds dt, which is the magnitude of the velocity. Now if we're moving along a circle here, we have that this is a constant velocity. The magnitude of the velocity is just r omega. Okay, so if we were to take the second derivative of that, since it's a constant velocity, the second derivative then would come out to be 0. So this coefficient would actually be 0. So the acceleration then would be just r omega squared times n. So the whole acceleration then is in that normal direction. You don't have any change in the speed, which is what the tangent direction would give you. So the entire acceleration is in that normal direction of the acceleration.